Morning, everybody. So, little note about the exam. I haven't graded it yet. I will do that this weekend, and I'll get you the results. But if you didn't do a exam redo on the previous exam, you still have that option this time. So, keep that in mind. I will have those exams back to you on Monday. And so you'll need to know Monday whether or not you want to do the exam redo, because it'd be due on Wednesday. So next week we have fall break, right? Thursday and Friday. So, and also I've still got to get you the stuff on the video project, and I'll get that to you later this afternoon. That'll be coming to you with a due date of Wednesday, and that can be emailed to me, so it won't be a problem for you to get that done. So today we need to jump into chapter 7. And so what we're going to start talking about is some elimination reactions. We're going to talk a little bit about alkenes. Alkenes, of course, have restricted rotation, and we're going to talk about mechanisms of elimination. So what we talked about last time, right, was we talked about nucleophilic substitutions, right, where a leaving group was leaving and a nucleophile was coming in. That's most of what we talked about. Okay, and so now we're going to talk about elimination reactions and see what we can do with those. So alkyl halides, as we mentioned last time, can do nucleophilic substitution reactions where the nucleophile, although it is a Lewis base, it is attacking a carbon atom, right? In elimination reactions, you're going to have an alkyl halide, but the base is going to function as a base and not a nucleophile, right? So my rule about bases, right, are nucleophiles. All nucleophiles are Lewis bases, but not all Lewis bases are nucleophiles. And so we're going to be finding some situations where we actually have Lewis bases that will function primarily as a base and abstract a hydrogen from the alkyl halide in a way in which you get an alkene. And so we are eliminating what? What are we eliminating in this process? Well, we're going to restrict the rotation, that's true, but what elements are we actually eliminating in this reaction? We're taking off the halogen and the hydrogen, so HX. H and a halogen, those are what? HCl, HBr, HI, what are they? They are strong acids, right? So we are eliminating a strong acid from an organic molecule to give us an alkene. What do acids like to react with? Bases, right? And so what do we need to do this reaction? We need a good base, right? That's the point here. So a good base reacts in such a way that you can eliminate a strong acid from an organic molecule and get an alkene. Now, if you look at this particular reaction, should the reaction lie to the left or the right, just by first principles? You think it should lie to the right? And why do you think it should lie to the left? Sigma bonds are more stable. That's exactly right. So we're going from a molecule that has more sigma bonds to a molecule that has less sigma bonds. Okay? So thermodynamically, it's not as favorable as the reverse reaction, but there are ways in which we can force the reaction to go to the right using things like Le Chatelier's principle, right? Things that you've learned about in general chemistry. So we know that the pi bond that we're creating is weak, and we're sacrificing 2 strong sigma bonds for that. The equilibrium should not lie to the right, okay? But we can force it to go to the right by using a variety of different tricks up our sleeve, right? And one of those tricks is to actually make sure that HX can't go backwards, right? And it turns out that if you take an alkene, when we start talking about addition reactions, HX adds to alkenes very, very quickly. And so somehow we've got to get rid of this HX as we're eliminating it, okay? And that's going to be another role of the base as well, okay? It's going to generate a species that doesn't readily do the addition chemistry, okay? So tell me something about, so we're eliminating a hydrogen and we're eliminating a halogen. If you had to use words and talk to your friends, which hydrogen is it that we're eliminating? Any old hydrogen, or is it a specific hydrogen? in the molecule? Okay, you're getting close. Actually, the closest hydrogens would be the ones that are on the carbon atom bearing the halogen, right? It's not those. It is the adjacent carbon, right? And so we have a special term for that. We call that the beta carbon. The carbon atom bearing the halogen we call the alpha carbon, alpha being first in the Greek alphabet, beta being second position, right, or in the Greek alphabet. And so you will quite frequently hear people refer to these as beta eliminations, where you are eliminating a hydrogen from the beta carbon and the halogen from the alpha carbon. What I have just told you is a critically important piece, because it means that's exactly where you're going to get your alkene. You're going to get your alkene between the alpha and the beta carbons. Okay? So that halogen is going to dictate to a large extent where your new alkene is going to be. So for example, if we take this particular molecule, and how would we name this? What would be the IUPAC name for this molecule? One bromobutane. And it's very important that I have the one there, right? Why is it important in my nomenclature that I have the one in the name? Pardon? Well, we do. That's right. So if I have the bromine on carbon number 1 and carbon number 4, or excuse me, carbon number 1 and carbon number 2, are they the same? No. One would be 1 bromo and the other one would be 2 bromo. What about if it was on the 4th carbon? It'd be 1. It's exactly right. So it would still be 1 bromobutane, okay? Because we're going to define our numbering system based on our substituents. So the numbering goes 1, 2, 3, 4, right? So we have 1 bromobutane here. And we are going to react this with what we call one of our favorite strong non-nucleophilic bases, potassium tert butoxide. It does not function as a nucleophile under normal conditions. Why does it not function as a nucleophile? What's that? Yeah. Yeah, it's crowded out. So we call this steric hindrance, right? So this is a bulky, non-nucleophilic base. So the basic atom is the O-, but it's got a lot of stuff around it. It would be very hard for this oxygen atom to get back here and kick out the bromine, okay, because it's bulky. But it can abstract a small hydrogen atom, okay? And when it does that, you end up with the alkene shown there. How would you name that alkene? It is 1 butene. That's right. But butene is the parent. It is 1 butene. Okay? Now here we have an example where we have, how would you name this alkyl halide? Chlorocyclohexane would be perfectly fine. Do I need a number? No, because no matter where I put that chlorine atom, it's still number 1, right? So that works just fine. Okay, chlorocyclohexane. But we could also name it as what? Cyclohexyl chloride. Both of those are perfectly valid names. Here we're using a base that also could function as a nucleophile because it's not terribly bulky. This is sodium ethoxide. But depending on the conditions, you can actually make this undergo elimination over substitution. Okay? Something you should know is that typically higher temperatures favor elimination over substitution. Okay, so typically we would maybe warm this up and boil it and force it to undergo the elimination chemistry a lot to a larger extent. And so how would we name the product here? Cyclohexane? Hexene, that's right. Cyclohexene. Notice the byproducts, right? What are the functional groups here for the byproducts? Okay, so that's a what? Okay, well, that's fair enough. It is a conjugate acid, but it's also what functional group? Hydroxyl's correct, but the class of molecules are known as alcohols, right? So we get an alcohol from the butoxide, and what's the other byproduct? A salt. Are salts typically soluble in things like organic solvents that we would do these reactions in? No, so what happens to them? They quite frequently precipitate out. And as they precipitate out, they can't form HCl or HBr or anything like that and make the reaction go back to the left. So by the precipitation of these salts, we can force the reaction to go to the right. And we're using whose principle? Le Chatelier's principle, right? So even though when we look at the bond energies, we would have predicted that the equilibrium should lie to the left, the fact that we're precipitating these salts out as the reaction proceeds forces the reaction to go to the right. And so we can use that kind of information to guess which way the equilibrium lies. Just about everything that you really needed to know you learned in about 3 weeks in general chemistry. Le Chatelier's principle is extremely important. Your acid-base chemistry is extremely important. Okay? And so don't forget all that stuff. It's good material to have. Okay? Now, when we're removing a hydrogen and a halogen, we call this dehydrogenation, in addition to beta elimination. You're going to find that us organic chemists, we throw out a lot of names. It really is, in part, you're taking a vocabulary class, okay? And so even though you might hear people call it beta elimination or dehydrogenation, you need to understand that these are really talking about the same things, okay? Now, if you'll notice, in this particular mechanism, the base, which is just generically written as B with a lone pair of electrons, so it can be potassium tert butoxide, it could be any number of bases, comes in on the beta carbon and abstracts a hydrogen, and those electrons that are in that carbon-hydrogen bond go to form the pi bond. These electrons are now going to be in the pi bond, and the leaving group leaves. So the base comes in, abstracts the hydrogen, these electrons move over here, and the leaving group leaves. 3 arrows are needed. So how many electrons are we actually pushing? We're pushing 6 electrons in this mechanism. The base is going after the proton is losing its electrons to form the pi bond, and the leaving group is leaving. Okay? What can you tell me about that hydrogen and that halogen? How are they oriented with respect to one another? They are kind of trans to one another. We don't call it trans, but they are kind of trans to one another. We actually call this anti-periplanar. Okay? Notice that the hydrogen that you have to eliminate has to be, if this is a plane, on the opposite side of that plane. Okay, 180 degrees, if you will, if you were to look at the Newman projection down that. Okay? Why does that make sense? Give me some reasons as to why that must make sense. Why isn't the hydrogen on the same side of the plane as the leaving group? Okay. So your argument is that if I have a halogen there, which doesn't have a negative charge, but it has lone pairs of electrons, right? And the base, which has a pair of electrons, and it may have a negative charge, right? If this was to work like this, right, these electrons would have to get really close to those electrons. And what do we know about electron pairs? They repel each other, right? You learned about that in Vesper theory. So that makes some sense, right? So this mechanism doesn't seem to hold water based on that alone. But there's another reason. It's a perfectly good explanation, but there's also another reason. Can anybody tell me what it is? Yeah, but that's too broad. No. When we did SN2 chemistry, how did the nucleophile have to come in? From the back side, right? So if we're just focusing on the alpha carbon, what's the nucleophile that's making this leaving group leave? It's not the base. The base isn't attacking the carbon. What's attacking that carbon? Not the hydrogen itself, but the electrons in that bond, right? And those electrons really need to come in from the back side, right? And why does that make sense, other than the fact that it kind of looks like an SN2 reaction? Why is it that an SN2 reaction had to have the nucleophile coming in from the back side? Huh? Okay, we've already addressed that part though, right? So, but what's the other part of the reason why the electrons have to come in from the back side? That's true. That's true. But why? I can push it on paper just like that. Why is that nonsense? That's true. That's right. We've got a bonding orbital and we've got an anti-bonding orbital, right? So the carbon-halogen bond, this bond really represents the bonding orbital, right? But these electrons, to break that bond, have to go into what? The anti-bonding orbital. And where does it exist? On the opposite side. So those electrons have to go into the anti-bonding orbital to break that carbon-halogen bond, right? It's real easy to think of this as coming in and kind of pushing out the leaving group, but it's all orbital driven, okay? And so this is where electron pushing can get us into trouble, because I can do this on paper perfectly fine. I've not broken any octet rules. I've not broken any rules of carbon, et cetera, et cetera. But it doesn't make any sense from an orbital perspective, because the anti-bonding orbital would be like this, right? And so these electrons have to come in and populate that anti-bonding orbital to break this bonding orbital and create the pi bond, okay? So, got to keep that in mind. So in this type of mechanism, the base needs to abstract the hydrogen atom that is anti-periplanar to the leaving group. And it's going to have very important mechanistic consequences on what types of products you have when we look at molecules that have more than one beta carbon, where we could get eliminations, okay? So you always need to keep in mind that it's going to be the hydrogen atom that is anti-periplanar to the halogen leaving group, okay? You need to know some of the common bases that we use in dehydrohalogenation. One of the most common bases that we use is potassium tert-butoxide. It is a good, strong, non-nucleophilic base. Has a pK of around 18 or 19. I can't remember the exact pK value. Higher than a typical alcohol. Okay? It doesn't behave as a nucleophile. So if you want to do an elimination, pick a base that can't function as a nucleophile. That's going to be potassium tert-butoxide. Okay? It is typically soluble, more or less, in simple organic solvents, like alcohols that we typically use for these types of reactions. Okay? Other common bases that are used, you will find examples in the literature of where they use just regular old sodium and potassium hydroxide. They've used sodium ethoxide, and they've used sodium methoxide. Actually, I pointed to the wrong one. Sodium methoxide and sodium ethoxide in these types of reactions. The problem with these bases, though, is what? They can also function as nucleophiles. So if you're going to use these types of things in eliminations, typically you have to have a substrate that itself is bulky or hindered so that it can't function as a nucleophile. For example, a tertiary alkyl halide. Okay? Or you have to heat it up so that it favors the elimination reaction. But we learned last chapter, right, that you can take sodium methoxide or sodium ethoxide in a primary alkyl halide and make an ether through an SN2 reaction. The name of that reaction was the Williamson ether synthesis. Okay, had a name associated with it. We didn't really talk too much about the name component of it, but that's the name of that reaction. okay? And so a primary alkyl halide plus an alkoxide from a primary alcohol typically does substitution chemistry. But if you had a secondary alkyl halide or a tertiary alkyl halide, they could be used quite readily in eliminations. Potassium tert-butoxide will not function as a nucleophile, so it's always your safe go-to bet when you're on an exam. Okay, if you need something that's non-nucleophilic and a base that's going to function in a way to do an elimination, most students will go after potassium tert-butoxide. It's a safe bet. Okay? Now, in this particular example, where we have a tertiary alkyl halide, okay, so this is 2-bromo, 2-methylpropane, and where do we know this from? Where have I used that for you before? I did. It was in the video. I called it tert-butyl bromide, right? And in that case, right, the bromide left, we got a carbocation and water attacked it to make an alcohol. We did an SN1 reaction, right? But in this case, where we have tert-butyl bromide and sodium hydroxide and maybe some heat, we can form an alkene. And this alkene, okay, there's only one alkene that can actually be formed, because it turns out that all of these beta carbons, even though I've got 1, 2, 3 of them, they're all what? It's up there. They're the same. They're all identical. So it doesn't matter which methyl group loses the hydrogen, you're going to get the same alkene. Okay? And you're going to form water as a byproduct, because the OH reacts with the hydrogen, and you're going to form sodium bromide, which falls out of solution. Another thing that drives this reaction to completion is the fact that this is a gas. This is a liquid, this is a gas, and so it removes itself from the reaction by bubbling out of the reaction mixture, and it can't go back. Only one alkene is formed. Okay? However, if we look at the bottom example, what we'll note is we find the alpha carbon. That's the one bearing the halogen. And we notice that this beta carbon is clearly different from this beta carbon. How are they different? They've labeled this one as beta 1 and beta 2. How does beta 1 differ from beta 2? Okay, beta 1 is a methyl group. That's true. And beta 2 is a? Well, the beta carbon itself is, beta 2 is not an ethyl group. It's part of an ethyl group, but how would you distinguish beta 1 and beta 2? I would say that beta 1 is a what kind of carbon? It's primary, and beta 2 is secondary. So remember, we learned how to identify primary and secondary carbons a few chapters ago. It's going to be very important here, because it turns out that the type of carbon atom that you have dictates which alkene you get. Okay? And so you can imagine if the base abstracts a hydrogen from beta 1, that you would end up with this particular alkene. And how would you name that? 1-butene. But we can also imagine a situation where the base comes in and abstracts a hydrogen atom from beta 2 and puts an alkene right here, and we end up with what? 2-butene, right? Are we going to get these in equal amounts? No, that is true. And if you had to base your argument on what you know now, which one would you predict to be the major component? The 1-butene or the 2-butene? You would probably predict 1-butene. And why would you make that prediction? Primary carbons might be easier to remove a hydrogen from. Okay, that's not bad. Okay, the primary carbon also has 3 hydrogens that it can choose to abstract from, right? Whereas the secondary carbon only has 2 hydrogens. Okay, you might make that prediction right now. Okay, it turns out that that prediction may or may not be correct, depending on the type of the base. If you use a huge bulky base like potassium tert-butoxide, you will get a little bit more of the less hindered alkene. But if you use a base that is not quite so hindered, you actually get the more substituted alkene. Okay, and we'll talk about why that is. Even with potassium tert-butoxide, if the conditions are right, you'll actually get the more substituted alkene. Okay, and so we need to talk a little bit about that. Okay, so you all will recall that a double bond, right, consists of both a sigma and a pi bond, and the pi bond is the weak component, right? Those electrons are above and below the plane of the two carbon atoms. Okay, so these carbons are sp2 hybridized, okay? And they are perpendicular to that plane, okay? The fact that we have a sigma bond and a pi bond tells us what about rotation around those two carbon atoms? It is restricted. You cannot rotate readily around that carbon-carbon bond. And so if we think of something like 2-butene, let's draw it up here. That is the quick and dirty way to write it. But how many products could we actually have? We can actually have two. We can have the situation where the hydrogens are on the same side. And we can have a situation where the hydrogens are on opposite sides. Cis versus trans. Those are different products. What kind of isomers are they? Are they constitutional? They are not constitutional. They are stereoisomers. They are not enantiomers. So they're not even mirror images of one another. So they're not enantiomers. So it's not R and S, but it's cis versus trans. They are geometric isomers, right? They're that type of stereoisomer. This one has a different boiling point than this one, different melting points. They give different IR spectra. They give different TLCs. Okay, they're kind of gaseous, so you'd have to do a TLC at really low temperature. But nonetheless, they do have different physical properties. Okay? You need to be able to identify what type of alkene you're getting. We just talked about cis versus trans, and that'll come back to haunt us a lot. But there are other types of alkenes that we can get. We can get an alkene that is what a lot of people will call a terminal alkene, which is at the very end. Okay, and so it only has one carbon atom attached to the alkene functional group. Okay, this is called a monosubstituted alkene. Okay, for those of you in polymer science, they refer to these as alpha olefins. You will learn that later probably, okay? Alpha olefins. And they are very, very useful in the polymer industry, materials industry. You can have disubstituted alkenes where the alkene contains two different carbon groups attached to the alkene. Now the carbon groups can either be attached to the same carbon or different carbons. It doesn't matter. Okay, we're just looking at one example here. We can have a trisubstituted alkene with 3 different R groups, and we can have a tetrasubstituted alkene with 4 R groups attached to the alkene functional group. Okay, they are all alkenes. They all have pi bonds, but they are not of equal stability. The reactivity of all of these things is different. So if we look, for example, at, let's see, 1, 2, 3, 4, 1-butene, it is a monosubstituted alkene. If we look at cyclohexene, it is a disubstituted alkene. And if we look at this molecule, we can see that this is a trisubstituted alkene. You just find the alkene and you count how many carbons are attached to the alkene. Here we have 3. Okay? So we can have monosubstituted, disubstituted, trisubstituted, and tetrasubstituted alkenes. Okay? Now, if you look at the rotation around a sigma bond, right, we know we can have different types of conformations. This would be the anti-conformation. This would be the eclipsed conformation, the methyl-methyl eclipsed, right? And we can look at these and look at certain projections. What were the name of those projections where we're looking at the sigma bond and looking at the different conformers? Newman projections, right? Okay, we have free rotation around sigma bonds. We know that. We do not have the free rotation around the pi bonds. And the fact that we don't have free rotation allows us to have these geometric isomers that actually have different physical properties. So how do we know that this is the cis isomer? The methyl groups are on the same side, right? And you can use that little corny thing I taught you about, on the same side. Right? That's cis. And here we have two methyl groups that are on opposite sides. This is the trans isomer. Which one of these would you predict to be the most stable if you were to build a model? You would predict that the trans would be more stable. And why would you predict that? We don't have any charges, though. That's right. So the same reason here, right? Exactly. This kind of looks anti like this, right? Where if we looked at the Newman projection, we know that having those big groups as far apart as possible was more stable. And the closer that they got to one another, the less stable, right? The same thing's going on here, right? This is kind of like the eclipse conformation in an alkane minus two hydrogens. And so those methyl groups are really close to one another, and they're not particularly happy that way. So in an elimination like this from an alkyl halide, would you predict that we would get more of the cis conformation in the alkene or the trans? You would predict that you would get more trans. And there are ways in which you can favor the cis over the trans. We'll learn about that more in later chapters. But it's a good bet that most of the time you're going to end up with that trans conformation being the most stable. Okay? And it turns out that these are diastereomers of one another. Okay? They have different physical properties. They are constitutionally connected the same, but those two methyl groups are actually located very differently in space. Okay? In the cis situation, they are together. The trans conformation, they are apart. And these two things do not interconvert readily. Having said that, we can interconvert them in the laboratory. We can go from the cis alkene to the trans alkene. If we take it and we put it in a quartz ampule and seal it and expose it to high intense UV radiation, you can convert the cis to the trans. Can anybody tell me what's happening in that process? Why would shining a bright, intense light on it allow it to go from the cis to the trans conformation? Yes. And how does that help me? It will break the bond. So what we're doing is we're going from a pi bond that is made, we're shining a bright light on it, and one of those electrons gets populated to a higher energy level, and that essentially breaks the pi bond. When that pi bond is broken, I only have the sigma bond holding everything together, right? And so what happens then? It has free rotation. And it can freely rotate, and then those two electrons can actually form the bond again. And now you go from a less stable conformation to a more stable conformation, and you can drive the reaction to the right. Okay? I actually have one of these really bright lights in my laboratory. It has to be liquid cooled. It's in a hood all by itself, because you will get an ultimate tan in like 10 seconds being exposed to it. I kid you not. I've been exposed to it before, and my vitiligo started to burn. Okay? Because and it was just for a second. It's really, really intense. Okay? These are called Hanovia lamps, and they generate a lot of intense UV radiation. And so we use it to do this type of chemistry where we have one conformation and we want to convert it into the more stable conformation. We can do that quite readily using that type of a light source. Okay? Anytime you have two groups on each end of the carbon-carbon double bond, you're going to have the possibility of diastereomers. Okay? So if we look at this where you have X, X prime, Y, and Y prime, we're going to have an opportunity for diastereomers. Okay? If X and X prime and Y prime are equal, there's no possibility of diastereomers. Okay? And this is really quite simple. Okay? If you have, on this carbon atom, X would be a methyl group, X prime would be a hydrogen. Those are different. And here we also have two different groups, right? Hydrogen and methyl. So we have the possibility of having two different diastereomers. And in fact, as we mentioned before, we can have the cis diastereomer, or excuse me, the trans diastereomer of 2-butene, and we can have the cis diastereomer of 2-butene. Okay? These have different stabilities. This is less stable than this. Okay? Because we're reducing these so-called steric interactions by having these methyl groups as far apart as possible. They're not occupying the same space. Okay? Not all alkenes are equally stable. The more substituents you add to an alkene, the more stable that alkene becomes. Okay, so something like ethene, which has no substituents, is less stable than a monosubstituted alkene, is less stable than a disubstituted alkene. Now notice that if we have the two substituents on the same carbon versus the two substituents on different carbons of the alkene, we say they're about the same stability, more or less. Okay? For all practical purposes, we can get away with that in this class. Okay? And these are less stable than a trisubstituted alkene, and a tetrasubstituted alkene is the most stable. So the more R groups we add to this, the more stable it is. How would we determine experimentally? How would we go into the laboratory and prove this or disprove it? How do you determine the stability of something? Let's see how long it takes to what? That could, it could have something to do with that, but what you're talking about when you're talking about time, we're talking about kinetics. And kinetics and thermodynamics are not exactly the same, right? So when we're talking about stability, we're talking about thermodynamics. So how can I determine the thermodynamic stability of something? Now, reacting has something to do with it. That's what she mentioned. Okay, so that's kinetics. Did you tell her to pay attention? She's paying attention. So we got the reaction part. We're going to do some kind of reaction, but what are we going to try to measure? We're going to try to measure delta G. And what are we going to, how do we do that? How did you all do that in general chemistry? In the laboratory? Okay, delta H, which is what? Which is kind of related to what? Heat. Exactly. So we're going to look at a heat of reaction, right? We're not going to look at seeing how fast it occurs, but we're going to look at see how much heat is given off when something like this reacts. Okay? And so we can think about a variety of different reactions to do with this, to do this type of chemistry. Okay? But one of the things we can do is burn them and measure the amount of heat that comes off when we burn these alkenes. So if I'm getting off a lot of heat, or if I'm receiving a lot of heat when this happens, is it more stable or less stable than something that gives off less heat? Less stable. That's right. The more heat you get out, that must mean that the starting material you were working with was less stable, right? Assuming we're getting the same amount of carbon dioxide and water for burning both of them. Okay, that goes without saying. Okay, but it's related, yes. Okay? So here's the example. Notice we have the different isomers, right, of this alkene. The number of carbons and the number of hydrogens is identical. Okay? So I ask, I don't know, let's say I ask Chase to take this one into the lab and burn it, which means he's just going to react it with oxygen, and he's going to get out of that, since it's a pure hydrocarbon, he's going to get carbon dioxide and water and heat. Right? So he's going to set up a fancy calorimeter. You all did the coffee cup calorimeter in general chemistry. You obviously can't use that here because these are gases. Okay? But you would use what's called a bomb calorimeter, which allows you to put the gas in there with oxygen and explode it and measure the heat that's coming out of the calorimeter. It's kind of a fun experiment to do. And what Chase would find is that he got on a per mole basis, he got 2,717 kilojoules of energy for every mole that was burned. And then I asked Jack to go and do the same experiment but use cis-2-butene. And what he would find in his measurements, he got the same amount of carbon dioxide, the same amount of water, but he got less heat on a per mole basis. Then I'd ask Kaylin to go and do the trans isomer this way, right? And what she would find is she got a little less heat than what Jack got, right? And then I'd give this one to Anna, and yes. And she would find out that she got the least heat, right? Well, they're pretty close when you're trying to do some comparisons. But in fact, they're not exactly the same, are they? So that little squiggly line depends on what the substituents are, okay? But what we could see is that the stability of these things isn't the same. Even though they all gave out the same amount of carbon dioxide and water, this one must have been less stable. It must have been higher up. And when it came down to that same floor here, if you will, right, there's more heat energy that was released, okay? So if you were trying to pick one of these to use as a rocket fuel, which one would you pick? You would probably pick this one. You want more heat, right? You want more energy coming out the back end of your rocket engine, right? And so if you were trying to build an explosive, which one would you pick? Less stable. That's why explosives tend to go boom real easy. They're unstable, right? But if you're wanting to build something that was more stable, something that would last a lot longer, like, let's say, I don't know, a material, right? You would probably pick something that's more substituted, right? Something like what you have over here, okay? So the reaction that we're doing is burning. We're doing calorimetry, okay? So we can determine the stabilities that way, okay? As you can imagine, there are two mechanisms for elimination. There's actually a third mechanism that we're not going to talk about right now. We'll talk about that at a later date. But for right now, we have E2 and E1. And these are very, very similar to the SN1 and SN2 that we learned about in the previous chapter. So I'm really not asking you to learn anything new other than the fact that you're going to get a different product. The kinetic parameters are the same. The things that go into determining whether or not you've got an SN1 or an SN2 are going to be very similar to whether or not you go through an E1 or E2. So things are highly related here. The big difference is that the nucleophile is not going to function as a nucleophile. It's going to function as a base, and you're going to get a different product, okay? So the E2 mechanism is a bimolecular elimination reaction, which means that the reaction is going to be dependent, or the rate of the reaction is going to be dependent on two things. And what are those two things? That's exactly right. So if you have an E2 elimination and you want it to go really, really fast, increase the concentration of the alkyl halide and increase the concentration of the base. Okay? E1 mechanism is going to be a unimolecular elimination. It's going to have the rate dependence on one and only one species. Which species will it be? The alkyl halide. The base does not come into the equation at all. Just like in an SN1 reaction, the nucleophile never came into the equation, did it? So from the viewpoint of the alkyl halide, everything's the same, it's just the products are different, right? So you don't have to learn any new rate equations, right? You just have to know that you're going to get different products based on the type of base you're using, okay? So in this particular case, if we want to avoid the SN1 and SN2 chemistry, right, and we wanted to favor the E2 and E1 chemistry, we better pick something that's not nucleophilic as our base, right? And that will favor the elimination, all right? So as we just mentioned, the rate of the reaction for an E2 elimination is going to be dependent on the concentration of the alkyl halide and the base. The reaction is said to be concerted. What do I mean by that? Okay, so the base is coming in, abstracting the proton at the same time that the alkene is being formed, at the same time that the leaving group is leaving. All of that is happening. And we represent that by how many arrows? 3 arrows. And we know that the hydrogen must be what with respect to the alkyl halide? Antiperiplanar. In E2 elimination, the hydrogen needs to be anti-periplanar to the leaving group. You need to have a non-nucleophilic base. The rate is going to be dependent on the alkyl halide and the base concentration. And how many bumps in the energy profile are we going to have? We're going to have one. It's going to go from starting material through a transition state down to the products. Okay, there's no intermediate. There is one transition state. Okay, in an E2 elimination reaction. Okay? And so we can depict that here, right? The base is coming in abstracting this hydrogen. These electrons are coming to form the alkene, and the leaving group is leaving. Now this base is pretty good as a nucleophile. Why is it not functioning as a nucleophile here? Exactly, right? So either my substrate can be sterically hindered or my base can be sterically hindered, or both of them can be sterically hindered, okay? But that's going to favor the E2. This cannot get back here to push out the bromide. It can only react with the small proton. And so in this case, you could pick a very simple base like sodium hydroxide to do this reaction. The only problem is sodium hydroxide really isn't soluble in organic molecules, organic solvents that we would typically do this, and the reaction would be kind of slow. But it could work, okay? And so this is what the transition state kind of looks like, or at least we believe kind of looks like. So here's the energy of activation, okay? Now, based on the Hammond postulate, does the transition state look more like the starting material or the product? The transition state, does it look more like the starting material or the product? Looks more like the starting material, because remember, whatever's closest in energy is what the transition state's going to kind of look like. So what are all these dashed lines? They're kind of like our arrows, right? This is telling me that we're starting to form a bond here. We haven't completely formed it yet, but we're starting to form a bond. And what is this telling me? I'm starting to break that carbon-hydrogen bond. And what about this dashed line? I'm starting to form the pi bond, and then this one? It's starting to leave. And all this is happening at once. So we call this a concerted reaction. Okay? There are a couple of other bases that you need to know that we quite frequently use in organic chemistry, because potassium tertbutoxide is a salt. Sodium hydroxide is a salt. Okay? All of those things that we've learned about the other bases were salts, and salts typically aren't highly soluble in organic solvents. And so there are times when we need a base that is highly soluble in an organic solvent. And there are many out there to choose from, but two that we think you really ought to know as a sophomore are DBN and DBU. I don't care if you know their real names, okay? D stands for diaza, B stands for bicyclo, N, nonane, and U, undecane. DBN, DBU, okay? And all you need to know is that these are highly soluble in organic solvents. They are non-nucleophilic, and they favor elimination chemistry. Now, I've got a nitrogen atom here with a lone pair of electrons, and I've got a nitrogen atom here with a lone pair of electrons on both of them. Your assignment for the weekend, because we're just about out of time, I want you to put this on a 3x5 note card for Monday, okay? I want to know which one of those two nitrogen atoms functions as the base. Only one of the nitrogen atoms functions as the base. Which atom functions as the base in each of them, and why? Okay, so you'll have access to the slide. You can use the internet. You can look things up. You have to give a reason why. Drawings would be greatly helpful. And if you're correct, I'll give you a bonus point that you can put on your exam. Okay? It is just 1 point, but every point matters. So, okay? Have a great weekend. Enjoy homecoming.